Hello, in the Why JTAL video, we describe why we need a good jitter tolerance JTAL in a CDR operation, but we haven't described how we should do the JTAL verification during the design phase. So in this video, we are going to show you the image of why we need a pseudo JTAL in a CDR design or verification. Before talking about the pseudo JTAL, let's review how the JTAL evaluation or characterization will perform. And the corresponding JTAL procedure is as follows. For each phase modulation frequency Fm, we may increase the phase modulation depth Am until the bit rate is violating. For example, pick Fm1 and Am1, and if we measure the bit rate less than the specification, for example, 1e-9 in DisplayPort or 1e-12 in the tangent-based KR protocol, then we can mark it as pass in green. Next, to pick Fm1 by Am2 and check if the corresponding bit rate passed the specification. The answer is yes, and then again, we can mark it as pass in green until we pick the same Fm1 by Am3 will cause the bit rate larger than the specification. Then we must mark the Fm1 and Am3 as fail in rate. In conclusion, we determine the maximum phase modulation depth Am is Am2 and stop the testing at the modulation frequency Fm1. Then we could keep the same procedure by sweeping other phase modulation frequency Fm from Fm2 to Fmn, and then determine each maximum modulation depth Am of each modulation frequency Fm respectively. The CDR JTAL would be complete after connecting all the maximum modulation depth in the blue line here. To make the ecosystem work in a series, most wireline standard would even define the JTAL mask as shown here. The CDR1 above the JTAL mask means it can tolerate more jitter than the standard specified jitter value to still meet the protocol's bit rate. On the other hand, the CDR2 can meet the JTAL mask at low frequencies, but not the high frequencies. Therefore, the CDR2 will fail the JTAL spec. Again, the CDR1's JTAL is better than the CDR2's JTAL. So, the CDR1 will provide a better transmission quality with less bit rate than the CDR2 does. After fully understanding how we characterize the JTAL, you may have a feel the bit rate will be an issue in a simulation. Why? Think about the bit rate images for 5 seconds. Bingo, the bit rate, or we could call the bit error ratio, which is the number of bits received in error divided by the total number of bits. Then we know the specification of the bit rate in tangent-based KR is 1e-12. What does that mean? Right, we must simulate the total number of bits greater than the 1e12 or 1000 bits to have a confidence that the 1e-12 bit rate target was covered. Not just that, remember the JTAL was checked the bit rate in each phase modulation frequency and depth pair. So we definitely cannot run any simulation, including the simplest CDR model in 1000 billion bits at each phase modulation. Not to mention to cover a few thousands of permutations or beyond in the phase modulation. So what can we do to have a similar JTAL in our simulation for the CDR design and verification phases? Think about the eye width images for 5 seconds. Correct. The link budget of the eye width can translate if we could meet the required bit rate with the defined jitter margin. Here is the summarized image of why we need a link budget from the analysis of eye width in the 30s. Since we know the bit array was not an efficient way in the system situation of the 30s. In addition, the link budget of the eye width will not only help us understand the ecological contributors and optimize it further during the design, but also let us know if we meet the bit array, if any impairments were needed to add later. For example, the total eye closure is 73% UI, so the link budget of the eye width is 27% UI to make the link meet bit array 1e-12 with a certain timing margin. If you do more link budget exercise, you could realize that link can even meet bit array 1e-15. On the other hand, we can even know the tolerable phase error between the data and clock phase would be 37% UI from the CDR's hunting jitter and total timing margin. Then we could conservatively use the 30% UI or 0.3 UI as the tolerable phase error of the clock data recovery CDR to still meet the bit array 1e-12. So think about the phase error Jitter image for 5 seconds. Yes, as the Jitter, by sweeping both the phase modulation frequency and depth in the peak-to-peak value, we can measure the maximum phase error between input data and output clock as we described in the white band loop dynamic analysis video. Instead of passing or failing the required bit array in the Jitter, the phase error is marked in the phase error Jitter image. In addition, as we mentioned, if we take the phase error equals 0.3 UI as a criterion, the 0.3 line could be the boundary between the passing or failing bit array 1e-12. Again, the beauty of the pseudo Jitter in the phase error is fast simulation time. Therefore, we can not only verify the band CDR by using the Jitter efficiently, but also help our band CDR design in several design parameters. Think about the first design parameter of the latency images for 5 seconds. Great. We can see the loop latency sensitivity as we discussed in the white low loop latency video, but with another Jitter point of view. As you can see, at the 100 MHz modulation frequency of input sinusoidal jitter, the ideal design zero latency would have 0.2 UI input jitter tolerance Jitter, and the real design Jitter is 0.18 UI, which is good enough. But if our poor CDR design with a 20 UI loop latency, the Jitter would be less than 0.1 UI and has a big jitter peaking shown here. So these Jitter images would let us know the importance of the loop latency. What else could we try? Yes, we could try the integral gain, which corrects the frequency offset. As we mentioned, if the integral gain is too much, and then add a stability concern as shown in the right-hand side poor design with a gain ratio of 3%. In this gain ratio integral gain to proportional gain Jitter sensitivity, we can put a proper integral gain without the stability issue. Anything else? Think about the input pattern image for 5 seconds. Right, as we mentioned in the white low loop latency video, the long pattern would add latency due to the missing data transition. Therefore, we could compare both PRBA31 and PRBA7 and see how the pattern impacts the Jitter. As you can see, the PRBA7's Jitter green line has a much better tolerance than the PRBA31 JTAL orange line as expected. In addition to the external impairments, what else of the internal impairments we like to look at? Think about the intrinsic VCO phase noise for 5 seconds. Yes, we must trade off the VCO phase noise and its power consumption. Therefore, with the pseudo JTAL images, we could specify how much the period jitter of the VCO we could tolerate and design for the corresponding power consumption. On the other hand, we could also evaluate our system level power budget to see if the power number is realistic for power saving mode by making the VCO noise higher without corrupting the CDR's normal operation. Here are the summarized images of why we need a pseudo JTAL in a CDR design or verification. The SerDes link will provide a better transmission quality with a low bit error rate or a good JTAL equivalently. Therefore, most standards even specify the JTAL mask for the ecosystem to follow. Even though the testing of the JTAL through the bit error is doable, it's impossible to run the JTAL simulation in any simplified CDR model to have the design or verification. Hopefully, we already have the link budget knowledge of the I width and know we could translate the target bit array to the final I width margin or the input jitter tolerance. So we could even plot a phase error based JTAL, which we call a pseudo JTAL here. With this useful pseudo JTAL, we demonstrate a few images of CDR's parameter, such as loop latency, gain ratio, input pattern, VCO noise, etc. to check the corresponding JTAL sensitivity, such that we could use as our design trade-off and sign off our design after this JTAL verification. Lastly, I hope this pseudo JTAL can help you to design or verify your CDR efficiently. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with people who may be benefit from it.